In this video, we will talk about multipath propagation and Rayleigh fading, and how to communicate over a channel that is Rayleigh fading. Well, for that, we will consider two categories. The slow fading case, where we'll define concept as the outage probability, outage capacity, and spatial diversity that we can get with multiple antennas. And in the fast fading case, we will consider the ergodic capacity and the concept of channel hardening that is appearing when you have multiple antennas. In multipath propagation, we have an antenna that is transmitting a signal to a receiver, and the radiated signal is spreading out as usual in all directions, but it makes it to the receiver not through a direct path, but through multiple paths where it's scattered on various objects here. In general, you could have a line of sight path in addition to all of these scattered paths, but in this lecture we will not consider that. So the line of sight path is blocked. However, there are all of these different objects that is providing us with additional paths that still makes sure that the signal is reaching the receiver. And what is categorizing these different paths is that they have a different length. So we have length D1, D2, DI, DL, each path have a different length. And the length is both meaning that we have a different attenuation for every path, both because of the length and because of the interaction with the materials that might be different for different paths. In the background video, we saw that when you have multiple paths, but you still have a narrowband channel, you can represent the channel from the transmitter to the receiver by a scalar that is a summation over the different paths. So we have capital L path in this case, and for each path we have two parts here. One channel attenuation, alpha I, and then we have an e to the power minus j 2 pi and a phase shift. Each path is represented by di, which is the length of the path, and that is determining how long time it takes for the signal to make it from transmit to the receiver, minus d, which is a reference distance. So the receiver is sampling its received signal at a particular time, and when the reference distance is d, a path that has exact the length d will be perfectly synchronized at the receiver side. But di minus d divided with the wavelength is telling us what will be the phase shift of that component. So we have these L different paths, and these will be interacting, leading to interesting phenomena that we couldn't see in the line of sight case. So as an example, suppose that we have capital L paths and each of them have a normalized attenuation, so alpha I squared is 1 over L. And then these 2 pi di minus d divided by lambda, we are calling this theta I. Since the difference in length among the paths can be many wavelengths, then this number here is much larger than 1. And if we take a number that is somewhere between 0 and some large number and wrap it into the interval 0 to 2 pi that is relevant when talking about phase shifts, well then we essentially have something that is uniformly distributed between 0 and 2 pi. And when the multiple paths with these kind of random phases are interacting with each other, we get what is known as multipath fading. So if we just compute the magnitude of the channel response, G, then we should have the magnitude of the summation of the paths. And in this example, alpha I was square root of 1 over L, so that the square of it becomes 1 over L. We have e to the power minus j theta I. If we now simulate how this looks like, what is the cumulative distribution function of the absolute value of G? If we have two paths, we get this behavior here. And what the cumulative distribution function is saying is that if we pick a certain number here along the horizontal axis, well, then the probability that the absolute value of G is smaller than that value is what we read out on the vertical axis over here. So this is showing the random variations. We get the dashed curve when we have two paths, and then when we have 8 paths, we get the red curve here, and if we have something that is called Rayleigh fading, we get the blue curve, which is very similar to have 8 paths here. So when we have at least 8 paths, well then it seems that the channel magnitude have a distribution that is very similar to what I called Rayleigh fading. And what is that? Well, that is if you let G be complex Gaussian distributed with zero mean and a variance that in this case is 1 because of the normalization that we're having, and then the absolute value of G has what is called the Rayleigh distribution. So why do we get this type of phenomena? Rayleigh fading is appearing in what we call a rich scattering environment. And it all boils down to what is known as a central limit theorem, which is a common theorem explaining why we see a lot of Gaussian or normal distributions in reality. So let x1 to xl be a sequence of real-valued, independent and identically distributed random variables. All of them have zero mean and the variance that we call sigma square. If we take these L random variables, we add them up, we are then dividing with 1 over square root of L sigma square, which is essentially 1 over the square root of the variance that we will have for the summation. Well, then this will converge when we have many random variables to a standard Gaussian distribution that have zero mean and variance 1. We can apply this result to analyze multipath channels, where L is now the number of paths. So now suppose that xi is the contribution of the ith path, so we have an amplitude here, and we have e to the power minus j theta I. And both the amplitude and the phase might be random variables here, and we can split it up like this, having a real part and then an imaginary part. And if we focus on the real part, well, then we can sum up all the real parts. We can apply this result here and say that the sum of the real parts will give us a Gaussian distribution. Then we do the same thing for the imaginary part and say that that one is also having a Gaussian distribution. One can show that the real and imaginary part will be independent of each other. And when we have a very large number of paths, we get the Gaussian distribution in both the real and imaginary part. And therefore the channel response G is complex Gaussian distributed and have some variance that we will call beta. And this model is called Rayleigh fading. Why? Well, if we compute the magnitude of G, it has what is known as a Rayleigh distribution. And in the Rayleigh distribution there's a scale parameter that defines it, just as in the Gaussian distribution there's the variance that is defining it. And in this case it happened to be square root of beta divided by 2, because this is a standard deviation that you have on the real and on the imaginary part. When analyzing Rayleigh fading channels, it's important to know that we have a Gaussian distribution, while the Rayleigh is mainly going into the name of it. We are seldom using the fact that we have this distribution in our analysis. But the Rayleigh distribution tells us that the amplitude of the channel, or the magnitude of it, is changing over time depending on which realization that we have for the moment. And here I'm showing a graph for the case when we have a standard complex Gaussian distribution with variance 1. So the absolute value of G will then vary from 0 up to some numbers here, and you see that above 3 here we practically never get. And here is the probability density function's variations. This probability density function might not seem so strange. We have some variations here from 0 up to say 2.5 to 3, and most of the probability mass is close to 1, which is the variance and standard deviation of G. But if we zoom in on the lower tail here, and we are changing so that we have a logarithmic scale here instead of a linear one. So we have 10 to the power minus 3, 10 to the power minus 2, 10 to the power minus 1, which is 0.1. We have 1 and we have 10. Well, then we see that the probability density function have a substantial tail down here. As I was pointing out, most of the probability mass is over here, where we have values close to 1. And when that happens, we have a fairly good channel, but there is a probability of being down at very small number, both below 0.1, well that happens 20% of the time, and being below 0.01, well that happens with a few percent of the realizations. And when this happens, we say that a channel is in deep fade. So at that particular moment, the signals that are propagating over the different paths are summing up in a way where the real parts are cancelling out each other, the imaginary parts are cancelling out each other, and therefore we get something that is very close to 0. And having a risk of having a very small channel gain, not all of the time, not even that often, but 5% of the time or something like that, is still a problem if you would like to have a reliable communication system. So there are these two issues, the variations in the channel quality and the unpredictability that makes it hard for us to adapt to those channel quality variations. We will now consider how the communication performance is affected by having these random variations in the channel. So we need to update our system model slightly. Previously, we were considering a discrete memoryless channel y of L was the received signal when we are transmitting a signal x of L. And then we were multiplying with the channel response g, but the new thing here now is that the channel response is not a constant, but it's also depending on the time index L. And then we're adding noise NL to it. So that is a new aspect, that g is time varying. Apart from that, we will consider that the signal is still complex Gaussian distributed and had some variance Q, which is measuring the energy per sample, which is the total power divided with the bandwidth, because the bandwidth is the symbol rate, and the noise is complex Gaussian distributed and have variance N naught. When analyzing the communication over a fading channel like this, well, then we need to consider how often is G changing? How much does it actually depend on time? And it's common to consider the two extreme cases in terms of that when analyzing communication performance. One is called slow fading, and that means that throughout our communication, GL actually only takes one realization. So the new thing is not that it's varying throughout the communication, but rather that it takes one random realization that we can't know in advance. The other category is fast fading. That means that GL is varying quickly, so that it essentially takes all its possible realization throughout our communication. Reality might be somewhere in between these two extremes, but we typically are analyzing these two separately in order to understand the important things that are happening in slow fading and in fast fading. So let us start with slow fading. So then the received signal y of L is a scalar g multiplied with the transmitted signal x plus noise. And we have a fixed realization in our entire transmission. However, it's the receiver who knows the channel, but not the transmitter, because the transmitter starts sending its data, and then the random realization of the channel is drawn, so the transmitter cannot know it in advance. For a given channel realization g, we know that the capacity, which I will now write as Cg, is log 2 or 1 plus the absolute value square of g, and then an SNR term here, which is Q divided by N naught. But we will write it as SNR in this lecture because we will not change this part, just to keep it simple. Since the receiver knows G, it can compute this value, but the interesting new thing is that the transmitter doesn't know G, so it cannot compute Cg. Therefore, we cannot achieve this capacity because the transmitter doesn't know how to encode the data to get this particular data rate. So how can we handle this situation? Well, the transmitter needs to opportunistically select the data rate. It needs to select something in order to transmit data, so it encodes data using a rate R bit per symbol. It pretends as if that were the capacity. Then there are two possible random events. One is that R, which is a constant, happens to be smaller than the capacity that we got for this random realization. And then we have a successful transmission, because if we can communicate at capacity Cg, we can communicate effectively at any rate lower than that as well. The other thing that can happen is that we happen to select an R that is greater than the capacity that we got at this particular moment for the realization G. And then we are not satisfying the channel capacity theorems, and therefore we cannot communicate reliably. We will have large error probability, and the transmission is essentially lost. When that happens, we say that the system is in outage. So that happens when R is greater than the capacity value that we have for this particular moment. And you might have heard the term outage being used when it comes to that the electrical grid is not working. Well, it's the same thing here. The system is not working at this particular moment. How can we handle this situation? Well, even if the transmitter doesn't know G, it knows the random distribution that it has. So that means that for every value of R, it can compute the probability of having an outage. And that is known as the outage probability for a given rate R. We will write it as P out, so P for outage, for a given R. And that is the probability that Cg is smaller than R. And Cg was log 2 or 1 plus the absolute value square of G multiplied with S and R, which should then be smaller than r. So this is how we define the outage probability. What I have presented on this slide is actually a general concept. It applies for any distribution on G. But what if we particularize the result for a particular distribution of G, namely Rayleigh fading? Since we have selected an S and R here, we can without loss of generality say that the variance is 1 on G. So let's consider that case. When computing this expression, we are utilizing the fact that the absolute value square of G is exponentially distributed with scale parameter 1, and this is then the CDF of something like this. When we are computing something like this, we are essentially taking the probability density function of the capacity CG that we are getting for different random realization. It has a particular shape. Then we select an R, which is the rate that we will communicate at. And then we look at all the probability mass that is on the left-hand side of this R under the graph. And this area is the P out. That means that as we are increasing R, we will of course get a larger area under the graph, and that means that we get a higher and higher outage probability the larger the rate is that we try to communicate at. We can see from this expression that the outage probability is a decreasing function of the SNR. And we want to operate our system at relatively high sync to noise ratios so we can communicate a lot of information. So in order to analyze even further what is happening at high SNR, well, if we have a high SNR here, well, then we have an exponent on e to the power minus the exponent here that is a small number. So we can apply a Taylor approximation that e to the power minus x when x is small is 1 minus x essentially. If we put it in here, the 1 and the 1 cancel out, and the x, well, that was the exponent here. We get 2 to the power r minus 1 divided by SNR. So we see that the outage probability is increasing with the rate exponentially, but it goes linearly towards 0 with the SNR. So the outage probability decays as the SNR to the power minus 1. And we should remember this behavior because we can utilize multiple antennas in order to change this scaling behavior. But before doing that, we will define something called the outage capacity. So what is the main difference from the capacity of a deterministic additive white Gaussian noise channel that we have considered earlier when the channel was non-fading or we had a line of sight channel or so? Well, the capacity is, strictly speaking, the largest rate that we can communicate at with 0 error probability. Since we have a random channel, the capacity in its original form is, strictly speaking, 0. There is no rate that we can communicate at without getting a fading realization that will lead to errors. So we need to find a balancing between having any data rate at all and trading away some reliability. And that is what the epsilon outage capacity is doing. So we denote it C epsilon, and it's the largest rate such that the outage probability for that rate is smaller or equal to epsilon. And we typically have equality here when we try to find the largest rate. So the interpretation is that with the probability 1 minus epsilon, we can communicate at this outage capacity with 0 probability, while with probability epsilon, everything fails. For the Rayleigh fading scenario that we have considered in detail, we can actually compute the outage capacity. So this was the outage probability that we obtained. If we say that it should be smaller or equal to epsilon, and we actually want to have equality here in order to make r as large as possible, then we solve this equation for r, and we get this expression. Log 2 of 1 plus the SNR multiplied with the term here, that is the natural logarithm of 1 minus epsilon to the power minus 1. And this factor is the difference from having an additive white Gaussian noise channel. It will be 1 if we have an additive white Gaussian noise channel, and now we have something that depends on our outage probability that we can accept. Let us compare this with the conventional capacity. Here I'm showing the outage probability, epsilon, from 0 to 1. The SNR is 0 dB. And here I'm showing the epsilon outage capacity. And as a reference here, I have the capacity for an additive white Gaussian noise channel. And when the SNR is 0, well then it is 1 bit per symbol. We can then see that for the Rayleigh fading case, depending on the outage probability, we are getting this curve here. Interestingly, the curves are intersecting at a particular point, namely when epsilon is equal to 1 minus e to the power minus 1. That is when this ln term is equal to 1. And when epsilon is smaller than that, well then the epsilon outage capacity is below the additive white Gaussian noise capacity, and it can be much smaller when we would like to have a small outage probability. While when we can accept a very large outage probability, we can get a larger epsilon outage capacity. This shows the dual nature of having a fading channel. It's sometimes good, it's sometimes bad. And if we need reliability, meaning a low epsilon, well then we take a big hit in terms of capacity here. We can communicate much more slowly than over a non-fading channel. But if we are opportunistically transmitting just part of the time, and the important thing is that we are then getting a high data rate, well then we can utilize this part here. But unfortunately, we don't know when the channel is good and when it's bad. So it's typically down here that we are going to operate. If we zoom in on this case here and consider the fraction of the additive white Gaussian noise channel that we can get, then we take the epsilon capacity here, divide with the additive white Gaussian noise channel, and we are plotting that number here for a varying SNR, and we are changing the epsilon value here. If epsilon is 0.1, so we can accept the 10% outage probability, then we get this curve here, and we see that when the SNR is low, we have a lot of problems. We only get less than 20% of the additive white Gaussian noise channel capacity. If we are increasing the SNR, we are getting a larger fraction of the additive white Gaussian noise channel capacity, but still only say 80% of it. And if we are reducing epsilon to just 1% outage probability, well then at low SNRs we are getting a very small fraction of the AWGN channel capacity, and even if we go up in SNR, we might only get like 60% of it. So in general, with slow fading, we get a much lower epsilon outage capacity than the capacity would have been for a non-fading additive white Gaussian noise channel. So can we improve the situation somehow? Yes, we can use multiple antennas. We will now extend the analysis to having multiple antennas at the receiver side. So it's a SIMO channel. So one transmit antenna here is sending out its signal. There is no line of sight path because it's blocked, and the receiver is surrounded by a lot of scattering object, which means that the signal is reaching the receive antennas from many different directions. If we consider just one of the antennas, then since there are many paths leading to that antenna, we can apply the Rayleigh fading model for that antenna. And we can do the same argumentation to say that each individual antenna have a Rayleigh fading channel to it from the transmitter. But what if we are taking all of the channels to the antennas here, stack them in a vector? Will the elements of this vector be independent? That is generally not the case, because the waveforms that are reaching this array comes from the same angles, so different elements will observe different superpositions of the same waves. But under some assumptions, in particular when considering a uniform linear array with half a wavelength spacing and having multipaths that are coming from all angles uniform distributed, then one can show that the individual antennas here are getting independent fading realizations. And that is one of the reasons why it's very common to consider uniform linear array with that antenna spacing in practice. Because we want to have independent fading so that we get as unique information at the different receive antennas as possible. So under these assumptions, we get a channel vector G, which is complex Gaussian distributed, have zero mean. Its variance, we call it beta. It's the same for all the elements because they are in the same propagation environment, and they are independent. So the covariance matrix is a scale identity. And we call this independent and identically distributed, or i.i.d, Rayleigh fading. We will utilize this model to study the outage probability, and then we know that in the capacity expression, the squared norm of G is showing up. And one can show that when the channel vector have this distribution, the squared norm have this probability density function. This is known as a chi-square distribution, or actually it's a scaled chi-square distribution because the variance is allowed to be just any number here. When we are utilizing this probability density function to analyze the outage probability, we will also consider this upper bound on it when the e to the power minus x divided by beta is omitted, because it's always smaller or equal to 1. So we can take it away and get an upper bound for every value of x that is greater than 0. So we will now consider M receive antennas and this i.i.d. Rayleigh fading model and quantify the outage probability. And remember, the outage probability for a given data rate r is the probability that the capacity that we get for one channel realization is smaller than this value r. And in this case, the SIMO capacity is log 2 or 1 plus the square norm of g multiplied with the SNR. And since we know the PDF of the square norm of g, we can rearrange this expression here. We can take 2 to the power of both sides to get 2r here. We can subtract 1, we can divide with SNR, we get this term here on the right hand side and the square norm of g on the left hand side. And then the probability that this square norm of g is smaller than this value, well, that is to take the probability density function and integrate from 0 up to that value. And then if you remember, I said that this PDF is a bit complicated to integrate. We can numerically integrate this in whatever way we like, but in order to get some nice expression, we use that upper bound on the previous slide. So we're integrating over something that is always larger, and therefore we get a larger probability. And when doing that, we get this expression. And one can actually show that when you have high SNR, we have close to equality here. But in any case, this expression is larger than the true outage probability. We have 2 to the power r minus 1 divided by SNR. It was this upper bound here, to the power of m, the number of antennas, and multiplied with 1 divided by m factorial. If you put in m equal to 1 here, we actually get the same value as we had before with one receive antenna. So what we called an approximation in that analysis was actually a true upper bound on the outage probability. So what we can see here is that the outage probability when we have m antennas is proportional to the SNR to the power of minus 1, or inversely proportional to SNR to the power of m. We call this factor m the diversity order. The reason behind that name is that we have m antennas that provide us with diverse, independent realization of the channel. And to have a deep fade, well, then we need all of them to be bad at the same time. Here is an example of what happens. We are showing the SNR on the horizontal axis, the outage probability on the vertical axis. The black curve is when we have one antenna. The red curve is when we have 2 antennas. And the blue curve is when we have 4 antennas. And you can see that at high SNR, we have this particular slope that I was talking about. That is different depending on how many antennas we're having. And while there is only a small difference up here when the SNR is low, at high SNR there is a huge difference in the outage probability depending on how many antennas we're having. And since we have a logarithmic scale on both the horizontal and the vertical axis, we can see the slope very clearly here as well. When we have a diversity order of 1, well then when we are moving 10 decibels to the right, we are dropping a factor 1 over 10 in the outage probability. So we have a slope minus 1. In the case of 2 antennas, when we are moving 10 decibels to the right here, the outage probability is reducing by 1 over 100. So that is a slope minus 2 here on the curve. And we have an even faster slope when we have 4 antennas. So when we have m receive antennas, the outage probability decays as the SNR to the power minus m, so it makes really a huge difference to have more antennas. Just 2 antennas makes a big difference, 4 makes even more, and so on. So what is the reason for that? Well, there are 2 phenomena that are appearing at the same time here. One thing is the beamforming gain that we talked before. So we have m receive antennas, they are collecting m times the energy, and therefore we are boosting the SNR by a factor m. So that would lead to a shift of the curves to the left so that we for a given SNR value get a smaller outage probability. In addition to that, we have the fact that the slope is different, and that is known as a diversity gain. So in addition to the beamforming gain that is sort of increasing the received signal power, diversity gain is reducing the variations in it, and that is because the probability that all the antennas are bad at the same time, or that all of the antennas provided with a particularly good channel realization at the same time becomes smaller and smaller. There is a behavior where we take the extreme, we remove them, and the square norm of G gets closer and closer to its average value. That was slow fading. Let's now move on to fast fading. Now we have this system model. For each realization of the channel, we receive YL, which is noise, plus the transmitted signal X of L multiplied with GL. So now the channel is changing with L. And we call this block fading because the channel can be constant for a block of symbol transmissions and then change independently. In practice, it might be constant for 10 or 100 different symbols. Now we will make it simple and say that we are changing it for every realization just to keep the analysis simple. Actually, the end result will be exactly the same. So in our case, for every L, GL takes a new independent realization, and we say that we have an ergodic random process that is generating that, which means that when we are looking at one instance of our communication system, where we get G1, G2, and so on, and we collect all of those realizations of G, well, it matches with the probability density function of G, and that is known as an ergodic process. So we will observe all the randomness that the channel has to offer during our communication. So in the fast fading case, the channel is varying very quickly. And how should the transmitter operate then? Well, remember, in the slow fading case, since the transmitter doesn't know the channel, it is selecting a rate, R bits per symbol, without channel knowledge. And it's the same thing here. We need to opportunistically select R. And during our communication, say that there are L fading realizations, G1 to GL, and then we will let L grow large. Then over L blocks, we will have reliable communication if the sum of the capacities that we are getting is greater or equal to the number of blocks multiplied with the rate that we are using. Then if we rearrange here, R should be smaller than 1 over L, and then we have the sum of the capacities for each of the channel realizations. So log 2 of 1 plus SNR, and then the absolute value square of G at time L. And if L now grows large, we can apply what is known as a law of large numbers, which says that if we take the average over an expression for many independent and identically distributed realization of something, namely the channel here, that sample average will converge to the expectation of it. So when the number of fading realizations L goes to infinity, this becomes the expected value of log 2 of 1 plus the absolute value square of G, now treated as a random variable, multiplied with SNR. And the expectation is then with respect to the randomness of the channel G. So this is a mean value with respect to channel fading. This value is something that one can compute at the transmitter even, given these channel statistics. This expression is called the ergodic capacity. And since we are averaging over many channel realizations, we are seeing all possible realizations throughout our transmission, this is a deterministic number. So even if the transmitter doesn't know the channel G, it knows the average value, this ergodic capacity value. So therefore it can select this rate, R, to match with this. So now there is no outage issues anymore. Transmitter knows perfectly how to encode this information. We can extend this to the SIMO case as well. Then we just are replacing the absolute value square of the channel with the squared norm of the vector channel in this case. Let us now compare the ergodic capacity for a Rayleigh fading channel with just one antenna. So we have that G is complex Gaussian distributed with variance 1. And this is the expression that we have in the non-fading case with an additive white Gaussian noise channel. So on the average, we have the same here, the SNR, the average of this expression is also equal to the SNR. But since the averaging, the expected value here is in front of the logarithm, these two expressions are generally different. On the right here, you see that the SNR is varying, and we show the rate here on the vertical axis. The solid black curve is for the non-fading case, and we have the Rayleigh fading case as the red curve. And at low SNR, they are overlapping. And that is because we can neglect the logarithm in that case, just move the expectation inside here, and then we are getting the same value. But as we are going up in SNR, there is a gap between them, and we have a lower number when we have Rayleigh fading. So there is still a penalty of having a fading channel in the fast fading case. So at low SNR, little difference. At high SNR, the ergodic capacity is lower than the corresponding additive white Gaussian noise channel. And one can actually quantify the gap. We are losing 0.83 bits per symbol at high SNR. And this has to do with the fact that the logarithm is saturating at high SNR. It's not growing linearly anymore. So when we have a bad channel, we are losing more than we are benefiting when we have a good channel. To quantify the impact of having multiple antennas, we will make use of something known as the Jensen inequality that you can apply to so-called concave functions. This theorem says the following: if we have a random variable set and a concave function f, then if we take an expected value of that concave function of set, then if we are moving the expectation on the inside, we always get something that is larger. So what is a concave function? Well, if you take a function, you draw a line between any 2 points on the curve here, and that line is always below the curve, then we have a concave function. So here's 2 examples. F a set of log 2 or 1 plus set. So it's essentially what we get in our rate expressions. It behaves like this. It's a concave function. And if we take this function, minus log 2 or 1 plus 1 over set, it has this shape, and this is also a concave function. And one way of verifying that something is a concave function is to compute its second derivative and check that it's always negative. When considering the ergodic capacity of a SIMO channel, we would like to compute the expected value of log 2 or 1 plus the square norm of G multiplied with SNR. And it's the square norm here that is the random thing. If we apply Jensen inequality and consider that we have this concave function f of set is equal to log 2 or 1 plus set, well, then it's the square norm of G multiplied with SNR, which is set. We can move the expectation into the inside. We get the expectation of the square norm multiplied with the SNR. If we let set be 1 divided by the square norm of the SNR, well, then it says 1 over set here. And we can apply Jensen inequality in the backward direction to get the lower bound in this particular way. And then we need to be able to compute the expected value of the inverse squared norm of the channel vector G. When G have i.i.d. complex Gaussian elements, then this expectation here becomes equal to m times the variance, which is 1. So we get m here. And one can show that this expectation here is equal to 1 divided by m minus 1, and therefore this entire term becomes m minus 1 times the SNR. And this holds for Rayleigh fading channels. This is interesting because now we have bounded the ergodic capacity of the SIMO channel between 2 values. The upper bound is equal to what we will get in a line of sight channel with m antennas. And the lower bound is what we get in a line of sight channel with m minus 1 antennas. So we are sort of losing 1 antenna. So if we are plotting these 3 different cases, then here we have the number of antennas from 1 up to 10. The red curve is the ergodic capacity, which you can compute numerically. The blue curve is the lower bound, and the upper bound is the black curve. And we see that when we have few antennas, there is a big gap between the lower and the upper bound, and the ergodic capacity is actually closer to the upper bound, but there is a gap. So there is a loss from having channel fading, just as before. And it could be around 0.83 bit per symbol, for example, at high SNR. But as we are adding more antennas, we see that the lower and upper bound gets closer and closer together, and then the ergodic capacity becomes even closer to the upper bound, which shows that the loss from having a fading channel becomes rather small when we have many antennas. And this is created by the spatial diversity that we talked about before. We have smaller variations around the average value of the square norm of G, and therefore the upper and lower bound becomes closer and closer together. And when we are talking about the ergodic capacity, this phenomenon is typically called a channel hardening. When the number of antennas m is large, there is really no penalty of having channel fading, because we know that even if each antenna is seeing an independent fading realization, the square norm of it will have very small variations left, and that is called channel hardening. In this video we have considered how to communicate over a fading channel in 2 canonical cases. In the slow fading case, we see one random realization of the channel throughout our transmission, and then we can define things as the outage probability and the outage capacity. And we saw that in order to get reliable communication, there is a large performance loss in terms of the number of bits per second that we can deliver. However, we can use multiple antennas to get a better reliability in the system. In the fast fading case, we see many different realizations of the random channel throughout our transmission. And then we can consider the ergodic capacity, which is a capacity concept where we are averaging over the fading. And then we don't get a reliability issue, but there's still a performance loss compared to having a non-fading channel. But when we have multiple antennas in our system, we can reduce that performance loss, and that is called a channel hardening effect.